Good morning. This is Dr. N. Ramya, Assistant Professor from Civil Engineering Department. Today my lecture is on momentum equation for boundary layer in hydraulic engineering. In previous classes we have discussed what is boundary layer and what is boundary layer thickness, and boundary layer thickness again it is divided into three types: displacement thickness, momentum thickness and energy thickness. These three thickness are all derived, and also we have done problems on it, right? So now here the momentum equation for boundary layer, this equation is given by von Karman, and this equation also called as von Karman equation, right? So here von Karman has proposed a method based on the momentum equation to analyze the boundary layer behavior. He has proposed a method which is based on the momentum equation, right? So here this method helps to determine this momentum equation method, that is von Karman's equation, is used to determine growth of the boundary layer along a flat plate, and second is a wall shear stress, third is drag force acting on the plate. And also this equation is used to approach is applicable. This approach is applicable when the velocity distribution within the boundary layer is known. When velocity distribution is known, this approach is applicable, right? And it can be applied starting from the leading edge to the edge of the flat plate. So in flat plate, this is your flat plate, and this is called a leading edge, and at the end we call it as a trailing edge, right? So here when a flow is moving to that flow, when you place a flat plate to that fluid, how the boundary layer will occur. We have seen all these things, right? So it is applicable from starting to the leading edge of the flat plate, right? This is what your boundary layer is. Yes, this is what your boundary layer is, and this we call as a boundary layer thickness. This we are calling it as a boundary layer thickness. This all we have derived in previous classes. So please, if you want, go through it. And this method is suitable for both laminar and boundary layers. So here in these boundary layer thickness, it is if the velocity of the flow is maximum, we see here two types of boundary layer thicknesses. One is laminar boundary layer thickness, and other one is your turbulent boundary layer thickness. Other one is turbulent boundary layer thickness. This is the turbulent boundary layer, and here it is a laminar boundary layer. This is laminar boundary layer, and it is a turbulent boundary layer, right? In this again turbulent boundary layer, again we have seen the small portion. That small portion we are calling as a laminar sublayer. This is what it is, a laminar sublayer, right? So it is suitable for both laminar boundary layer or as well as turbulent boundary layers, right? So this is von Karman is used to determine all these things, and applications also here we have seen, right? Here fluid flowing over a now we are deriving a von Karman equation, momentum thickness equation, right? So here for this fluid flowing over a thin flat plate, fluid over a thin flat plate, right? Fluid is flowing over a thin flat plate with free stream velocity equal to u. This is what your free stream velocity. This is what your free stream velocity u, capital U. when this free stream is entering on these flat plate, we are seeing some variation in velocity distributions. Velocity distribution at velocity here it is 0, and as you move further, there is an increasing in the velocities. So at one point, the velocity is becoming equal with the free stream velocity. Yes, let us say this inside velocity is a small u, and outside the velocity before entering the flat plate, the free stream velocity is capital U. Free stream velocity is capital U. And here entering on the flat plate velocity is small u, right? So here, when these velocity distribution, velocity variation will becomes a mainstream velocity, that is, when u is becoming your capital U, or u is equal to 0.99 of your capital U, free stream velocity, that is nothing but u is equal to capital U, right? Then these complete distance thickness we call as a boundary layer thickness. Boundary layer thickness is where the point of it is a distance from the boundary to where your velocity is becoming your free stream velocity. When velocity is becoming your free stream velocity, that is equal to u is equal to capital U. Small u is equal to 0.99 times of your capital U. This is the condition. This is what your boundary layer thickness is, right? So that is what fluid is flowing over a thin plate, and we are seeing placed at zero incidence with a free stream velocity equal to u. Right? Inside it is small u and outside it is capital U. Now consider a small length dx. Consider a small length dx of the plate at a distance x from the leading edge. From the leading edge. Consider a small length dx of the plate at a distance x from the leading edge. The enlarged view of the small length of the plate is shown. Right? Considering small unit width of the plate perpendicular to the direction of the flow. Right? These things we see now in image. Right? This is what image is. So this is what your flat plate, flat smooth thin plate. It is capital U is your free stream velocity, which is having the velocity before entering to the fluid, right? When it is entering, we are seeing the variations in the velocities. That variation we are determining by small u, right? Where your u, small u is becoming capital U, then that distance we call as a boundary layer thickness, right? Boundary layer thickness. So what we are doing here, from one point to, we are taking a section AD and another small distance we are taking BC, small a box like structure, small element we are taking. This is what, that is the distance from leading edge to the point is x, and the small element which we have taken, that is your dx. This is a dx, and the way we are taking from the distance from point to element. That is what here written. Small dx, small length of the dx of plate is at a distance x from the leading edge. The enlarged view is of the small length of the plate is shown here. See, now this ABCD is shown here. This is what here small portion is enlarged. That is, the length of the small portion is dx. Yes, on that, this is what here, this is the velocity distribution. What is this? This is a velocity distribution. This blue one is velocity distribution. In that velocity distribution, we are taking a small strip in y direction. That is what? Here dy. That is dy. And from the plate to the vertical distance dy is here small y. Here small boundary layer thickness, right? It is dx is a distance of the small element from A to B, and from this A to D, we are taking a velocity distribution. In that velocity distribution, we are drawing a small strip, that the thickness of the small strip is dy, and from the point to the dy it is small y, and complete it is velocity boundary layer thickness, right? Now for this we are deriving a momentum equation, right? To this we are deriving a momentum equation. This is what the shear stress. Tau naught is your shear stress. When velocity is 0, the shear stress is maximum. Yes, shear stress is minimum, vice versa. When shear stress is minimum, your velocity is maximum, right? So this is what a shear stress is, tau naught. Now here, to the element A, B, C, D, the small element, the enlarged one, this is what here let A, B, C, D be a small element of a boundary layer. The edge DC, this is what the edge CD represents the outer edge of the boundary layer. See here, this is what AB, CD, right? So AB, CD. So what is here? AD is the fluid entering and BC is the fluid where it is leaving, right? So here we are calculating first mass rate. Why? Because here momentum is mass into velocity. Mass into velocity. So first we are calculating a mass rate of fluid flow through AD is what 0 to integration of 0 to boundary layer thickness delta. The fluid which is inside the ADBC having the density rho, and inside the velocity is the fluid flowing with the velocity small u and with respect to dy, the varying velocity with respect to y. So it is a small element, that is dy. So integration of 0 to delta rho into small u into dy. That is what the mass flow rate which is entering into AD. The mass flow rate which is entering into AD. Now mass flow rate we are calculating for BC. For BC, which is fluid leaving at a section BC, right? So here integration of 0 to delta rho u into dy plus, and the differential portion here it is adding to this rho u dy plus d by dx into integration of 0 to delta rho u dy into dx, because this complete length it is considering. So what the equation is becoming, a mass of the fluid entering at AD, that is equal, and here the small portion, that portion is integration of 0 to delta rho u dy plus d by dx integration of 0 to delta rho u dy into dx with respect to in this direction, that is x, and small portion dx. That's why we are writing as a dx, right? Therefore, the mass of the fluid entering the control volume through the surface DC. This is DC, control volume entering through the surface DC. So here what we are doing, we are subtracting a BC minus DC. This is what BC minus a DC. This is A, B, C, D, right? So A, B, C, D. Already this in BC minus AD. This BC minus AD. Already we know this. This is AD, the distance, and here the small distance, right? So here we are subtracting the rate of from BC DC. This we are subtracting from mass flow rate of DC. So what it happens to this integration of 0 to delta rho u dy plus d by dx integration of 0 to delta rho u dy into dx minus integration of 0 delta rho u dy. So this and this will get cancelled, and here we get this equation, this one, d by dx into integration of 0 to delta rho into u into dy into dx. That is what the equation we got. So the fluid is entering through DC with a uniform velocity u. Here the velocity is entering with u. Till here it is a boundary layer thickness. At this point the velocity is becoming here mainstream velocity u. So here in place of small u, you can write for this DC this portion as a capital U, right? So now we are calculating momentum rate of fluid entering through the controlled volume in x direction at AD. Now first again same we are doing, we are a fluid entering through the AD, right? Fluid entering through AD is, momentum is what? Mass into velocity. So already we have calculated mass flow rate, that is what? Integration of 0 to delta rho u dy into u, small u. It is entering through the AD, that is small u. So what happens? Complete momentum equation is 0 to delta rho u square into dy. That is what a fluid entering momentum equation, which is entering the fluid, is integration of 0 to delta rho u square into dy. Now momentum rate of fluid leaving control volume in x direction. Control volume in x direction. So through BC, right? So here in place of single u, in place of mass, into you can add velocity so that you will get momentum equation. Momentum. So 0 to integration rho u square into dy plus the differential that is d by dx integration of 0 to delta rho u square into dy into dx in x direction, that is dx. This is what your momentum equation is, right? Now momentum rate of fluid entering the control volume through DC in x direction. DC in x direction, right? X direction is capital U. The fluid flowing in this is, the velocity is u, right? So d by dx into integration of 0 to delta rho u into dy into dx into u. This we got by doing a mass momentum rate of fluid BC minus AD. You will get this and this will get cancelled. Only this equation will be getting d by dx into integration of 0 to delta rho u square into dy into dx. This is what our rate of fluid only entering through the BC minus AD. This is the equation we are getting. And that equation we have written here. And here one more thing, we are writing here in place of DC, the velocity is capital U. So whatever the equation we got, that we are writing d by dx integration of 0 to delta rho u dy into dx into capital U, because in this fluid we are seeing velocity as a mainstream velocity. That's why we are writing capital U. So the equation becomes d by dx integration of 0 to delta rho u into capital U into dy into dx. This is what the momentum equation, which is in fluid entering to the controlled volume of DC in x direction. Now we are calculating rate of change of momentum of control volume. This control volume. The momentum rate of fluid through BC. First BC. This is BC. Minus AD. This minus AD. And momentum rate of fluid through DC. This DC. so that this is what momentum through, and this is what a momentum at AD, and it is momentum at BD. Now, when you differentiate, you will get this 2 gets cancelled, and leftover is this and this, right? So here is what this and this is getting cancelled, right? So the only term left is d by dx integration of 0 to delta rho small u square into dy minus integration of 0 to delta rho small u into capital U into dy into dx, right? So here, what are the common things we are taking out here? D by dx, first integration is taking common. Integration of 0 to delta rho u square into dy minus rho u capital U into dy. This integration is taking first out into dx. After that, and what are the common things here? Rho is the common in both, right? So I am taking rho first outside in this. D by dx into rho integration of 0 to delta u square minus small u minus capital U into dy into dx. And rho is constant for incompressible fluids. So what they have did, complete rho as taken outside, rho into d by dx, integration of 0 to delta, u square minus small u capital U into dy dx. Right? This is the equation we got. So from this, as per the momentum principle, the rate of change of momentum on a controlled volume ABCD, this is what a controlled volume ABCD, must be equal to the forces on the controlled volume in the same direction. And ABCD must be equal to the forces, total forces on the controlled volume in the same direction. The only external force acting on the controlled volume is the shear force acting on AB in the direction of BA. Direction from B to A. This is what a shear stress is. B to A, only external force. The value of these force is given by the drag force is what? Shear stress into the distance, that is dx into dx. The drag force is shear stress into dx. And total external force in the direction of rate of change of momentum is tau naught into dx. So here tau naught into dx, that is equal to rho into d by dx integration of 0 to delta u square minus small u into capital U into dy into dx. Now we are taking this dx. So what the term is left? Integrate tau is equal to minus dou into dy dx integration of 0 to delta u square minus u capital U into dy. Right? That is equal to rho into d by dx into integration of 0 to delta. Here it is a minus sign because here it is my signature is minus here because it is moving in B to A direction, it is opposite direction, so that's why we are taking minus tau naught into dx. So minus tau, the direction minus, so that's why when it is taken to the right hand side, it is becoming minus rho into d by dx integration of u square minus small u capital U into dy. So I don't want here minus signature, so I am taking this minus inside. So that equation is becoming rho into d by dx integration of 0 to delta small u into capital U minus u square into dy. U capital U minus u square into dy. Right? So rho into d by dx integration of capital U square. I want this complete in terms of U by capital U. So what I am doing here, I don't want here. Here I am writing U square. U square I am taking common. So what the equation is becoming? U square on both sides, numerator and denominator. So what your equation is becoming here? Here I am taking u square on both sides, right? So your equation will become u square common, u capital U minus u square into dy. This is what your equation is without this 4u minus u square into dy, right? So here I am taking complete u square to get in terms of u by capital U, right? So here I am taking u square common and the equation is becoming u by capital U minus u square by u square. Yes, when I am taking this u square outside, this u will go and down here u will come, right? So u by u capital U minus u square by capital U square into dy, right? So u by u, again I am taking u by u outside complete common. So u capital U square d by dx into integration of u by small u as small u by capital U 1 minus small u by capital U into dy. Right, I am taking this common. So what is this inside one is integration of small u by capital U into 1 minus u by capital U into dy is this complete is momentum thickness. This complete one is momentum thickness, right? So yeah, these both will taking on the left hand side so that your equation has become tau naught by rho u square that is equal to d by dx of your momentum thickness. This is what your momentum thickness. So the equation has become tau naught by rho u square is equal to d theta by dx. This is what a von Karman equation is. This is what a von Karman momentum equation. The above equation is called as a von Karman momentum equation for boundary layer flow and is used to find out the frictional drag on smooth flat plate for both laminar as well as turbulent boundary layer. This is what a von Karman equation is. And here, the boundary layer condition, the following boundary layer condition must be satisfied for any assumed velocity distribution, right? So your two conditions we have taken at the surface of the plate, the distance y is 0 and your u is also, velocity is also 0. So what happens to your du by dy? It is infinite, it is finite value. It is finite value. And second condition is what? At the outer edge of the boundary layer, at the outer edge, your y is becoming your delta, and your small u is becoming capital U. At that point, the velocity is changing to the free stream velocity, right? So, and your y is equal to delta and du by dy is equal to 0. So, du by dy is equal to 0. Then the shear stress for the given velocity profile in laminar, transition and turbulent zone is obtained from this equation. What is that equation is? Shear stress into area, drag force, shear stress into area, tau naught into B is the width of the plate and into dx. Here the width of the plate we are taking as a unit, that is B is equal to 1. Therefore, your shear stress into dx is equal to your drag force. Your drag force, tau naught into dx. So, the total drag force on the plate of the length one side is integration of 0 to L distance tau naught into B into dx. This is what the equation for the drag force on a flat plate. Now, another equation, that is the ratio of the shear stress. This is what the equation is, coefficient of skin friction, or we call it as a local coefficient of drag. So local coefficient of drag is the ratio of the shear stress tau naught to the quantities half rho u square. Half rho u square is known as a local drag coefficient, right? So what? And it is denoted by CD. Coefficient of drag. Local coefficient of drag is what? Tau naught by half of your rho u square. And here the ratio of total drag for the quantity of half rho a u square is called average coefficient of drag, and it is always denoted by CD, that is FD by half rho a u square. Here one term is getting introduced, that is your area for average coefficient of drag. In above it is only rho u square. Only rho u square in local coefficient of drag. Here, for average coefficient, it is area of the plate into u square. Right? This is what average coefficient of drag is. Here are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.